Okay, so that was a cartoon example of what this theory proposes. What I'd like to do now is to dive into one real example of how this theory should work and how sort of this idea of continuity and discontinuity with other species plays out. I will take as an example number cognition, so the ability to sort of understand the number. Now, with respect to number cognition, the theory goes as follows. We come into this world with two particular modules that are relevant to number cognition. And these are old core knowledge modules. So these are modules that we possess, but that other species also have. And these two modules are first, an analog magnitude system. This is often referred to, you might have heard it called the number sense. The ability to kind of look at, a number of dots on a wall and kind of get a sense of its numerosity. Is it really, really a lot, or is it just a few, or sort of just, you don't count them, but you kind of get an idea that, oh, that's a lot, or that's little, something of that sort. As I said, often referred to as the number sense. The second module is known as the object individuation system, also known as subitizing. And the idea with this module is that instead it allows you to represent exactly a couple items, typically between 1 and 3, maybe 4. And in fact, without having to count. So you look at it and you immediately know it's 1, or you immediately know it's 2 or 3. So in a sense, if you think of it, these two modules operate on very different types of representation. On the one hand, you kind of get an idea of set magnitude. I don't know precisely what number that is, but it's either a lot or medium or a little. So that would be your number sense. The object individuation is more, oh, here's one item, or here's 2 items, or here's 3 items. And it's the object individuation or subitizing is a very precise idea of how many individuals are there. 1, 2, 3. And you don't even need to count them. You know instantly that it's a specific number. The analog magnitude system, on the other hand, it's coarse. It doesn't give you an exact number. It gives you an overall impression for just how much. And now, as I was saying, the theory says that these are two core modules that are old and that we come into this world with. So we have them as infants before we acquire language, but also other species, in fact, several other species also have these modules. So this is the continuity part of the theory. But let's take them one at a time. Let's first look at the analog magnitude system. Let's look at a couple examples in the number sense. For example, if you take infants, somewhere around 5 to 6 months old, you can use a habituation paradigm, just like the one we've already seen. And you can see if they can recognize approximate numerosity. So the way in which this works is exactly the way we saw it in the context of color cognition. So you would show, you would again put an infant, in a baby chair and in front of a screen. And on the screen in front of them, you might show, a pattern of dots on the screen. And it's a certain numerosity. Let's say, 16 or something like that, or 8, something like that. And then you show the same numerosity again and again and again and again. And notice that the dots that you project don't have to always be in the same position. You can move the position around of the dots. What matters is how many there are. Okay, the fact that the numerosity is constant. And just like we saw in the color experiment, the time that infants spend looking at the screen goes down with repetition. So the more you repeat the same numerosity, the more infants sort of get bored because they know what it is. They've already seen it. So they habituate. And now, just as in our color experiment, What is interesting is if you show them the same numerosity again, typically infants keep being bored and not looking much at the screen. However, if you now show them a different numerosity, or rather something that they might, recognize as different, maybe you were showing 8 dots on a wall and now you show 16, suddenly the infant perks up and now looks at the screen again, which makes us think that the infant recognized that this is a different numerosity. Again, it's not about the precise number, but overall there's a sense that this numerosity is different. The set contains, either more or quite a few more or quite a few less than the set they habituated to. So this is a nice example of the fact that we come into this world with an understanding, even before we acquire language, with an understanding of approximate numerosity, again, or the number sense. Turns out the same idea can be looked at in several other species. For example, in the rodent model, you can put an animal inside a so-called Skinner box, if you remember that from the beginning of this lecture series. And the way in which you would test it is that you would put a lever and you would connect the lever to a reward system so that the reward is only delivered after so many presses. And the way in which it works is that the animal has to press, I don't know, let's say that the reward is delivered after 10 trials, have to press 10 times, then they have to wait a moment, and then the reward is delivered. Okay. So this ensures that they don't just keep pressing until the reward is given. They learn that they have to press, let's say, 10 times, then stop pressing, and then they're given the reward. So how well do they do? Well, this is the result from one such study. So if you set the reward to occur after 4 button presses, in general, the animal seems to press just about 4 times, or maybe 5. Okay. And what is interesting to notice is that at the numerosity of 4, they do very well. They are 25% of the times they press it 4 times, 25% they press it 5 times, and then sort of, other numerosities they only press fewer and fewer times. Now set the numerosity, set the reward to occur after 8 button presses. What you see is that again, on average, they seem to press 9 times, more or less. So the peak is 9 times. But they press 20% of the times they actually press 8. 23% of the times they press 9. Another maybe 18% of the time they press, 18% of the time they press 10. So it's inexact, but overall they kind of got the approximate numerosity. And again, notice that it's fairly coarse. They don't understand exactly 8. It's kind of in the vicinities of 8, right? It's an approximate number system. And then you do the same thing, but now the reward occurs after 12 button presses. And again, notice that now, so 12 is here. So just about 14% of the time they press 12. Maybe 18% of the time they press 13 or 14 times, and then another 13 or 14% of the times they press 15 times, etc. And notice that again, the higher the number becomes, the coarser the representation, the vaguer the representation. Again, this is an approximate numerosity. So like it's around 8-ish or 16-ish, or okay, it's not an exact number. And the larger this number becomes, the more your sense is just, ooh, that's a lot or that's little. And indeed, if you make 16 the number after which they're given a reward, you can see that they press, 10% of the times they press 16, 15% of trials they press 17, maybe 15% of trials they press 18, etc., etc. But see how the distribution, the representation of magnitude becomes fuzzier and fuzzier the larger the magnitude. I mean, think about it. If I showed you dots on a wall, if I show you just 4, it's easy to tell. If I show you 8, you kind of get a feeling for it. But by the time I've shown you, 16, 18, 30, 76, you don't have an exact understanding of how many dots there are. It's just oh, there's a lot, or there's little, or there's sort of middle. But again, this does show that in both pre-linguistic humans, so infants, before they've learned language, and in obviously non-linguistic species, the analog magnitude system, or the number sense, is already there. And that's, again, this is why we are continuous with other species. We have these same domains, these same modules of knowledge. So that was the analog magnitude system. How about the object individuation system? And again, as I said earlier, this is really about the ability to perceive individuals, to perceive something and say, oh, this is a one item, and then say, oh, this is one and one, or this is one and one and one and one more. Okay, and this is the sphere within which this module, also known as subitizing, seems to work. And you don't have to count them. You just look at it and you immediately know it's 2, or you immediately know it's 3. You don't have to sort of count them one by one. So this again relates to the ability to detect, small numbers, precise numbers of individuals. So again, is this indeed a module that we have and that other species have? Same experiment as before. You put an infant, you put them in front of a screen, and now you simply habituate them with 2 dots or 2 objects versus 3 objects. So same as before, maybe you show them, 2, 2, 2, 2, 2, 2, and they slowly lose interest and look less and less at the screen. What's interesting is that, again, if you show them again the number 2, they again don't have much interest in it. But if you now show them the number 3, suddenly they perk up and they seem to look more at the screen. And then, of course, if you keep repeating it, they slowly lose interest. And the same is true if you habituate them with 3 and then show them 2. So definitely pre-linguistic infants do show subitizing. In fact, and this is part of the module, it's not just the understanding of sort of one and one and another, but also you can make calculation, simple calculation with these small numbers. And again, this is an exact representation of small numbers. So not only you can just look at them and tell how many there are, but you can also make, as I said, small number calculations. Here's one example, again, in young children. It goes like this. So there's a little case, and the child is seated in front of it. The infant, rather, is sitting in front of it. A hand comes in and brings in, a little object, maybe a Mickey Mouse or a puppet or something like that. And this is in full view. Then you raise a screen so you can't see what's here. And then you see another hand come in with a second object, and sort of it pushes it in all the way to here behind the screen. And then you can see the hand leave empty. Now here's what's interesting. Then one of 2 things happen. Either the screen comes down, and indeed there are 2 little objects, which is exactly what you'd expect. So this is a possible outcome. Or by magic, the screen comes down and there actually is only 1 little object, despite the fact that they saw one come in at the beginning and then they saw a second one come in. Obviously being there a small trapdoor here by which they can remove one of the objects without being seen. And you can do this both with addition. So this is a case where you do 1 plus 1. And then you can do the same with subtraction, right? There are 2 little objects that come in, then the screen comes up, and then an empty hand comes in. It takes one object and you can see the one object leave. And then the screen comes down, and in the possible outcome, there's only one object left, which is what you'd expect. In the impossible outcome, the screen comes down and there are still two objects, which of course should not have been the case. Turns out, in both this addition context and this subtraction context, children look at the impossible outcome for longer, as if they were thinking, wait, that's not right. Or at least they notice that the possible and impossible outcomes are different outcomes. And typically these are interpreted with the child looking longer at the impossible outcome, implying that that is not what they were expecting. But this does show that children can both identify very, small numbers, so 1, 2, 3, before they acquire language, and they can also do exact small number calculation way before they acquire language. Now, the same can be seen in non-human primates. So in this experiment, rhesus monkeys were shown something very similar to the previous one, except it was done with with grapes, I believe. So the setup is the same. There's one area here, and there are 2 bits of food, maybe 2 grapes, and then here there's a single piece of food, and the monkey can see this. Then a screen comes up, and the monkey sees the experimenter take one item, even though the animal doesn't see anymore the grapes. They see the experimenter take one grape and move it on the other side. And then, although they're not seeing how many grapes there are on either side, they have to just go towards either one or the other in order to receive the reward of the food. Turns out, almost always, animals go towards the one that has 2 grapes. So clearly they could understand, they could do this kind of a small number exact calculation.